In Lab 4 of Physics 2211, we focus on oscillations. The purpose of this lab was to observe the motion of a mass attached to a spring and analyze it using Tracker. We then used the data provided by Tracker to create a computational model in GlowScript, which is then compared to the observed model. The results of this lab found that both the models for the x and y positions were similar and that the change in energy is zero. Important concepts in this lab are Newton's second law, which states that the net force acting on an object is equal to the change in momentum over the change in time, and the energy principle, which states that the total change in energy is equal to the sum of the work done by the surroundings and the transfer of thermal energy to the system due to the surroundings. Here are the formulas used in this lab. These formulas will be present in our GlowScript code. Here is a model of our experiment. The system is the Earth, the spring, and the mass. There are no surroundings. Here's the video showing the tracker analysis of the motion of a mass attached to a spring. This is the data gathered from the tracker analysis. The mass of the object is given by the preview video and is 0.402 kilograms. The initial position is negative 0.128x, negative 0.639y, and 0 c meters. The initial velocity is 0x, 0y, 0 c meters per second. The initial time is 0 seconds, and the final time is 9.497 seconds. For the computational model code, we use the initial conditions given by the tracker analysis and insert it into the code. The values of Ks and L0 are given by the preview video, and the formulas of K, Ug, Us, and E are derived from the formulas mentioned earlier. Here is some more code for our computational model. These are the graphs that were created from running the code. As you can see, the change in gravitational potential energy is the opposite of the change in spring potential energy. This is seen in the graph with the green and red lines. As one increases, the other decreases. This causes an oscillation. In the two position versus time graphs, the x and y positions of both the observed and computational models were compared. The y position versus time graph had very similar values for both models, indicating a very accurate prediction. The x position versus time graph was also similar, but it has some deviations and was less accurate. Potential errors that could have led to this deviation are forces and energies that were not considered, such as drag, and inaccurate tracking due to the placement of the center of mass. The energy system is satisfied as shown by the graph. The value of delta E is the sum of delta K, delta Ug, and delta Us and should be equal to 0. The orange line in the graph shows the value of delta E, and it is 0. To calculate the oscillation period, you need to measure the change in time between two crests or two troughs. By measuring each one, the average can be found, which is 1.618 seconds for the x position and 1.572 seconds for the y position. The difference between the two is 0.046 seconds. This difference could have been caused by unconsidered forces or inaccurate tracking, and the difference itself can affect the calculation of spring constant, spring force, and spring potential energy.